Kia ora, and welcome to lecture 3 of week 2 for 162.04. The topic today is solving first order linear equations. So last time we did solving first order separable equations. So now there's a different method for solving a different class of equations, namely a linear equation. But we can solve, because they're a bit simpler, we can in fact solve all equations of this type. All linear first order equations, we can solve them. Those functions a1, a0, and g will come up, and we'll have to integrate them or something like that as we go. Now, just to motivate the method, I'm going to try and solve this one here first. X squared dy dx plus 2xy equals 4. It looks a bit nasty, but it's actually not as bad as it looks, because the left-hand side is in fact a derivative of something. What is it the derivative of? It's the derivative of x squared times y. Let's just work that out. First term is a product here because y is some function of x, so it's a product rule. How do you do the product rule? You go first term times the derivative of the second term plus the derivative of the first term. Derivative of x squared is 2x times the second term, which is exactly what I've got on the left hand side. And the right hand side I don't need to do anything with, it's just equal to 4. So this says the derivative of x squared y is 4. Well, that means that x squared y itself must be the antiderivative of 4. Well, that's easy to work out. That's 4x plus c. So I'm done. I've solved the differential equation. I can even solve explicitly for y. Divide both sides by x squared. I get 4 over x plus c over x squared. Done. Now that was very special though, because the left-hand side, for that to work, the left-hand side had to have exactly the right form, that those two terms were the derivative of something coming from the product rule. Now that's not going to work for this one. It doesn't have quite the right form, but there's a classic mathematical trick, which is to do something to that equation so that it looks like the one you already knew how to solve. If you compare this example with the previous one, they're very similar. If I multiply both sides by x, on the left-hand side, I've now got x squared dy dx plus 2xy equals xg of x. In this case, I'm not telling you what the function g of x is. It could be any old function. So by multiplying both sides by x, the left-hand side is now a derivative of something, and I know how to solve it. That says the derivative of x squared y is xg of x. So x squared y must be the antiderivative of xg of x. So that more or less, I can't work out that integral because I don't know what the function g of x is, but that more or less has solved the differential equation because there's no derivatives of an unknown function in there anymore. So that is the foundation of the method of solving linear equations. You have to multiply the equation by something so that the left-hand side becomes a derivative of something by the chain rule. Now I'm using the word something, something, something in there. Luckily there's a formula that tells you how to do that. We're going to discover the formula, but once it's been discovered and written down, you just need to use that formula. Okay. So, how would this work? Well, the first thing to note is I've got this coefficient in front here. I don't really need that. I can divide the entire equation, divide both sides by a1 of x, assuming that is not identically 0. And then I'll just have an equation starting with dy dx. So that's called the standard form. So to do that, you divide by a1 of x if necessary. Put the equation in standard form. And I'm going to multiply both sides by something, and I don't know what the something is yet, so I'm going to call it I of x. It's called the integrating factor. Which is a bit tautological. It's just the thing you multiply by which lets you solve the differential equation. So I get I of x dy dx plus I of x p of x, y is equal to I of x f of x. And I want the left-hand side to be the derivative of something. What should that something be? Well, if you remember the previous example, it was the derivative of I times y. That's how the previous example worked, and that's how it's going to work in general, because that's the only way I can get that first term there, is if when I differentiate this by the product rule, I get first term times the derivative of the second term will give me the I times dy dx. And that means I must have the derivative of the first term times y must equal I of x. Whoopsie, didn't want a y there. What was I doing? Let's back up a step. This is I of x dy dx plus di dx times y, match terms, this term must equal this term because this term is already equaling this term. So I get the y's match, and I get di dx equals I of x p of x. So that's the equation that I would have to satisfy for this method to work. So unfortunately, or fortunately or unfortunately, it's a differential equation for I, but it's the kind that I know how to solve. It's a separable one. So that is good. So I move the i's to the left, move the dx to the right, integrate both sides. I'm done. Antiderivative of 1 over I with respect to I is log I. I don't know what p is yet. It will depend on the particular equation. I'm not actually going to write the plus c in here because I just need one function I that will work. I don't need all possible solutions. So I get that the integrating factor must be e to the integral of p of x dx. Now the point is this: you don't need to go through these steps when you're actually solving one of these differential equations. You just need to use this little formula for the integrating factor, and then you're done. So you do need to remember this formula. Let's put some little rivets in it there. It's a very important formula. Once you've got this formula in your pocket, you can just use that formula, work out I, multiply both sides by I, and then, hey presto, you'll be done. There we go. So let's just use that method on this equation. dy dx plus 3x squared y equals x squared. First check that it's in standard form with no function of x in front of dy dx. Yes it is, that's good. That means the integrating factor is e to the integral of p of x dx, which is e to the integral of p of x is just whatever the coefficient of y was. Integral of 3x squared is x cubed, so the integrating factor is e to the x cubed. Multiply both sides by that. E to the x cubed dy dx. Oops. E to the x cubed times dy dx plus e to the x cubed times 3x squared y is equal to e to the x cubed times x squared. This left-hand side will be a derivative of something. What is the something? It's just the integrating factor times y. And at this point you can pause and double check that that has worked out. What's the derivative of e to the x cubed times y? Use the product rule. It's e to the x cubed times dy dx, that's my first term, times the derivative of e to the x cubed, or from the chain rule, that's e to the x cubed 3x squared, times y. So it does work out. So that means that e to the x cubed times y must be the antiderivative of e to the x cubed times x squared dx. How do I do that integral? It looks a little bit nasty, but that's a substitution one. So I'm going to make u is equal to x cubed. Du is going to be 3x squared dx. So 1/3 du is x squared dx. So if I make that substitution, I get integral of e to the u times x squared dx, which is equal to 1/3 du. So that is 1/3 e to the u plus c, which is 1/3 e to the x cubed plus c. Do I have any more space? No, it's gone. My solution is solve for y by dividing by e to the x cubed. I get y is equal to 1/3 plus c e to the minus x cubed. Okay, we'll do one more example. If you are very keen, you can pause the video and have a go at doing this one yourself before I do it. So let's go. It's in standard form because there's nothing in front of the y prime. So the integrating factor will be e to the integral of the coefficient of y. So e to the integral of minus sine x dx. The integral of minus sine x is cos x, so I get e to the cos x. Oops, that's the answer. Multiply both sides by that, I'll get e to the cos x dy dx minus e to the cos x sine x times y equals e to the cos x times 2 sine x. You must take care to multiply both sides of the differential equation by the integrating factor. The left-hand side must be a derivative, and sure enough, it is the derivative of e to the cos x times y. That is well worth stopping and checking at this point. I'll let you do that. E to the 2e to the cos x sine x. So that means that e to the cos x times y must be the antiderivative of 2e to the cos x sine x. So once again I get to practice integration by substitution. This time I want to make u equal to cos x, so that du is going to be equal to minus sine x dx. I look at my differential equation and I see sine x dx there, so that means I really want minus du is sine x dx. Make that substitution where sine x dx turns into minus 1 du. I get minus 2 integral e to the u du. That's minus 2 e to the u plus c. That is minus 2 e to the cos x plus c. And I'm done. I found the implicit solution. Now in this case I also have an initial value, y of pi over 2 equals 1. I could either solve for y first, or I could substitute it, and I think I'll solve for y. It doesn't look too bad. Divide by e to the cos x, I get y equals minus 2 plus c e to the minus cos x. If I substitute in x equals pi over 2, y equals 1, I get 1 is equal to minus 2 plus c e to the minus cos pi over 2. Cosine of pi over 2 is 0, e to the 0 is 1, so I get minus 2 plus c. 1 equals minus 2 plus c, so c is equal to 3. So the explicit solution is y is equal to negative 2 plus 3 e to the minus cos x. Okay, very good. Thanks everybody, and absolutely essential step now is to go away and practice the method of solving first order linear differential equations. Kia ora.